Okay, so imagine a world where software writes itself, bugs are fixed before they occur. You don't need to worry about pull requests, code inspections, regression tests on that update, or even the deployment in a CI/CD system. And project timelines are met with uncanny accuracy. You know, Gartner predicted that 80% of all the software development tasks that are required in a engineering lifecycle will be affected by AI. And GitHub was brave enough to say that 30% of all new software will be AI generated. Well, these are no longer predictions. And what I said before is no longer science fiction. This is the world of software engineering today enabled by artificial intelligence. My name is John McKinnon. I am the Software Engineering Vice President at Ciena. My responsibility is for the Network Navigator Control Suite, which is a very comprehensive software system that we built over the last 7 years to manage the network. It's a fully multi-layer domain controller, as you can see, as an object model from optical layer 0, OTN, Ethernet, and IP services. Provides very comprehensive data management of those services and has a comprehensive user interface to power that and enable the operator. We also have applications that provide analytic insights, and of course, it would be complete if we weren't saying we're transforming all of that with AI ops, putting a large language model on the front of that so that humans can interact with the system, and using machine learning and algorithms for better prediction and optimization of network data. But I don't want to talk to you about AI ops. I want to talk to you about how we build that system and the engineering tasks involved in building a big software system like this. My engineering team at Ciena has a capacity of about 30,000 person weeks per year. And our estimates, using the AI tools that we use today, is we can achieve about a 25% development productivity improvement on that development, which means, to me, I get a 7,000 person week saving every year. Now, actually, that's not a saving. We're not looking to reduce our R&D investment in this suite by 25%. What we want to do is reinvest that productivity gains to get even more output from our software development engineers so we can go quicker, faster, and build even more sophisticated applications within our engineering team. And that's what we're doing. Let me just take a step back and tell you why I think AI has such a profound impact on software engineering. It goes back to the fundamentals of what a programming language is. And if you think about it, a programming language is about translating the input to a CPU, which at its basic level is ones and zeros, to stimulate the control logic, the memory, and the output that you require, which is calculations and logic transactions. That's fundamentally what the CPUs of computers are meant to do. And of course, the first level of abstraction of that language was assembler language. When I was a software engineer in college 40 years ago, that's what I used. That's what I learned as a programming language. That translates the ones and zeros into alpha letters, so hexadecimal. So now I can program a CPU in hexadecimal code rather than ones and zeros, making it easier to program a CPU. Now, as you go through the history of programming languages, in the 80s we had COBOL, which actually then used letters to words, so now I can program that CPU in a word abstraction. Java became very popular in the 90s. That takes words into tasks, enabled machine-independent programming, and provided the way of building event-driven programming for the first time. And then in the late 90s, early 2000s, we had Python, which abstracted the complexities even further, so the complexities of programming became even more applicable to individuals, and scripting became very popular in Python. You didn't have to understand all of the complexities of the CPU in order to write a pretty powerful Python script. But nothing's really changed in the last 20 years on that computer programming stack until today. And the application of large language models to software programming has now provided the ultimate abstraction into that basic CPU, which means anybody can talk to a computer processing unit in the language of us, our human language. I can instruct the computer to do exactly the output that I'm hoping for in a human language way, which means all of this stack below may be obsolete. So what happens to our software engineers? Now we have that complete abstraction, and I can talk to a CPU in my own language. Well, the analogy I'll try and use is the one of the pocket calculator. This invention came through another technology advancement, which was the single-chip microprocessor, and through that advancement, we were able to put machines, handheld machines, calculation machines, into everybody's accessibility. So calculation machines were no longer just for the few in big rooms. They were available to everybody in a handheld device, which meant everybody was able to perform complex mathematical calculations. And it saved orders of time in terms of magnitude in that calculation process, and of course improved the overall quality of the output of mathematics. But did this mean that the mathematicians disappeared? No, absolutely not. It meant that the mathematicians were able to spend more time on the bigger systems, the bigger problems, and use the calculator and the calculation machines to do the tedious tasks and the remedial tasks of calculations, saving time and improving the quality of the output. And I put it to you that AI will have a similar impact on software engineering. Yes, sure, everybody can now instruct a chatbot to create a software application, but really, in order to solve the bigger system problems, like we need to do when we're building network management systems for complex IP networks, we need software engineers to think about those things and then use the tools to do those things much more efficiently. And that's what we're doing within our engineering group at Ciena. I'll just give you a taste of that in this diagram here. This is the software development lifecycle that we use that explains all of the different processes and steps into the engineering process. And I'll start with how we're using AI in each one of those. Start with education. We found that AI systems are extremely effective in analyzing code that's already been written and summarizing the functions and features of libraries or processes for junior engineers who are coming on board and coming up to speed with what the applications actually do. And we've used it in training new grads and new people onto the project very effectively by using the output of AI tools to analyze existing code. And that's probably the most effective immediate impact we've had in our development process. Of course, the second one, code generation. That's the one that's very obvious, probably top of mind for most people, is how do we use it to generate code? We found it's very good. AI is extremely good at translating from one predefined interface to another predefined interface, mapping functions. It's extremely good at mapping things from one domain to another, or doing upgrades. So upgrading, again, from a language or a third-party library and doing the changes required that are version updates on dependent software packages that are part of the system. We have tried it out for other code generation tasks, but as we'll talk about in a minute, if you don't give it the right context and the right domain, we've had varied results. We've also seen varied results on code generation depending on the language. So some of these tools are very good at certain languages and not very good at others. So you've got to be careful with how you use AI for code generation. But for some of the remedial tasks, it's very good. Code inspections, this is probably one of the most popular ones, probably the most tedious and loathed activity of our software engineers today is to do a code inspection. They're very slow, they're very ineffective, and it takes a long time to get them done. So we're using AI tools to do a code inspection on a pull request. And that does syntax checking, context and compatibility checking with the pull request at the time that it's submitted to the code, and they're making suggestions to the designer of what should be changed in order to get it correct. And this has had a dramatic impact on our productivity. Another area of dramatic impact is on testing. So the test engineers we have, their job is to write test cases for the software that is built as part of our system development. But of course, those test cases have to explore all corner cases, all the eventualities, all the error paths that are part of that software structure. Using AI to look at all of those different combinations and corner cases and generate the test cases automatically is proving extremely beneficial for the efficiencies of our test engineers. And you still need to know what you're doing, so you still need to make sure that the tests are actually directed at the right problems. But with guidance, we can achieve an incredible impact on test engineering. We also found that bug fixing and bug detection using AI examination tools is very effective. We've had examples where we were looking for a defect for a number of days, we couldn't find it, we threw it at an AI tool, and in 5 minutes we found out what the problem was. And again, that can be a dramatic impact on customer satisfaction, but also the frustration of the software engineers. So using it for bug fixing is very effective and can contribute to those savings I mentioned before. Finally, analysis. So using an agentic AI framework that we're using internally within Ciena, we're looking to combine findings from all of our log results, large system test, even our customers' field issues, bringing that all together and trying to derive what is the correlation between this information that could drive us to a better design in the product in the future. So designing for supportability, designing for bugs that we think are recurring, and correlate that information using agentic AI frameworks is very effective. We're also looking at how we can use that framework to automate this cycle that I show on the board here. So those are all individual steps, but if you put an agentic framework together, you can then automate not just the steps individually, but the linkages between the two. And you get to the vision that I was just talking about at the beginning. So, sounds great, but there's always a but, and this is the but slide. You've got to be careful. The intellectual property and ownership of code generated by a large language model is still up for debate. There are still legislations, indemnifications are given by some of the language model providers, but to be honest, I'm not sure they're worth anything, the paper that they're written on, or they will stand up in scrutiny. So we're being very careful about what we generate in terms of our code that goes into the product, and certainly we're not claiming IP and title ownership of that software because that's something that still could be very volatile. So intellectual property you've got to be very careful with. There's also an increase of copyright infringement, so bringing in other things from the language model that may be copyrighted, and now all of a sudden find themselves into your product, so you've got to be careful with that. Large language models can write buggy code, so it doesn't always make it correct. And in fact, what we found is that guiding the system and prompt engineering is extremely important to make sure that the AI systems are directed at the right problem and giving you the right result. So it needs oversight, and it needs engineering oversight to make sure you can get the benefit of that automation. Just talk about, so the thing I like to say when I'm talking about AI in engineering is, yes, with great power comes great responsibility. There is not a free lunch here. It's not automatic. You've got to be careful with what you do. Just a thing on prompt engineering. So this is very important, and I think this is one of the areas that every engineer needs to understand is the importance of how you can prompt an AI system to get the output you want, and that's around clarity, context, and constraints. And if you can focus on those three things, then you can get the right results and the right automation out of AI systems in software engineering. Basically, the better you are at prompt engineering, the more you will get out of these AI tools. I think we all have that experience with GPT as well. So, my final conclusion and my final slide is that my belief today is that AI will not replace software engineers. But software engineers who use and leverage AI will replace those that don't. Thank you.